give it a second. Okay, so we have started recording, and just for safekeeping, okay, now you're set. So let us start with this concept of traction. So I mentioned this concept of traction very briefly and in a very light mode back when we were doing our chapter number 0, that is that review chapter at the beginning of the semester. So let me just quickly discuss it once again, but in a slightly more detailed fashion. So right now you have to change your thinking, okay, little bit. You try to put your mindset back in the mindset which you had while studying physics, okay, while studying physics and mathematics. Okay, so very general scientific kind of thing. When I'll have to ask you to change your mindset to more like an engineer, I'll explicitly ask you to do that. For now, think like a scientist. All right, so consider a general three-dimensional body. Okay, general three-dimensional body. Now we are not referring to any particular axis or anything. What we are going to refer to is just a general plane, a cutting plane, which is going to cut this three-dimensional body. So this plane is like this. So this plane cuts this three-dimensional body into two parts. We will call this lower thing region 1 and this upper part region 2. And we are going to focus our attention on the part of this region 1. So it will look something like this. Where this flat surface is the flat surface that is generated by that cutting plane. Now imagine that this entire three-dimensional body is acted upon by a variety of forces. Okay, forces, couples, whatnot. Okay, distributed forces, various things. So let me just depict forces only. Okay. So the same things will appear here. Now, if this region 1 has to be in equilibrium, see, understand that the whole thing is in equilibrium. Here also this thing has to be in equilibrium, which means there must be a distribution of forces which are exerted by the region 2 on the region 1. And those forces will be distributed on this flat plane. Fine. Now we are not going to consider the entire flat plane. Rather, we are going to focus our attention on a certain point within this flat plane. So let us call that point here. Let us consider this point here. Okay, this is not any centroid or anything like that. Okay, some arbitrary point. It can be here, 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 here. Okay. Now, next what we do is we consider a small area around this point. We focus our attention here. It's a very small area. For the sake of clarity, I have drawn this thing large like this. So if I just isolate out that thing, it will be looking like this. Please note that this area is this small area. Okay, this is not that entire flat plane. I'm just zooming into this. And on this area, there will be a certain distribution of forces which are exerted by the region 2. Something like this, like this, like this, like that. Since this is a distribution of forces, by our knowledge from first year basic engineering mechanics, we can say that this distribution of forces may be equivalently represented by one force and one couple. Same area. But this time represented by a force and a couple, like that. Let this force be F vector. Let this couple be C vector. Now what we do is we say that we are now going to start shrinking or making this area smaller and smaller. We are going to start shrinking this area or making this area smaller and smaller to the limit that it tends to 0. In that case, what is going to happen is that the distribution of forces that you see over here spread over this finite area, that distribution of forces is going to change as we start shrinking the area. Consequently, the magnitude and the direction of this force is also going to change. Similarly, the magnitude of this couple and this direction is also going to change. Ultimately, in the limit that this area tends to 0, this magnitude will reach a finite value. Okay, and this couple, what is going to happen to this couple? Who can tell me?
Becomes 0.
Why?
It tend to 0, sir.
Why?
The resistance from force is 0.
Distances are tending to 0.
Exactly. So this couple is actually arising because of a moment arm times a force, or a couple of forces multiplied by the distance between them. Now, if you keep on shrinking this area or making this area smaller and smaller, that distance is going to reduce. And in the limit that the area tends to 0, that distance is also going to tend to 0, or the moment arm is going to tend to 0, which implies that this couple is also going to tend to 0. So what we say is like this, that as the area tends to 0, so we say that this is the area A, this is the area A tends to 0. What happens is that the magnitude of C, it tends to 0, and the magnitude of F, well, it becomes smaller, but it still remains at a finite value. Now is the important part which will enable us to define this traction. So what we say is that the traction denoted by this T vector, traction is equal to limit of F vector divided by A, as the area tends to 0. So the traction vector is equal to the force vector divided by the magnitude of the area as the area tends to 0. Fine. So you may be thinking that back in your earlier days, you probably called this particular entity to be the stress itself, that force divided by area is stress. So because you are now growing older and older, you have to define things in a far more precise fashion. So the actual official proper mathematical definition associated with this entity is not the stress, but the traction. So this is traction. All right. However, since you have discussed earlier or you have studied earlier that there is something to do with stress whenever you are talking about something like force divided by area, it must be true that there must be some kind of relationship between this traction and the stress. And that is true. There is a relationship between the traction and the stress. It is not a direct equality, however. So we are going to study that relation, and it is through that relation that we are actually going to take our first step towards our next topic, which is the transformation of stress. So we are going to spend quite a bit of time, unlike the previous chapters where we finished up our theory in about half an hour or 45 minutes practically, and then we started discussing problems. Here we have to spend quite a bit of time discussing the intricacies of the underlying theory itself. Because if you understand this theory very, very nicely, solving the problems will become quite straightforward. Okay, and it is absolutely essential for you, especially as mechanical engineers, to understand this very, very important topic, because the way that we are going to discuss it it will be so very general that it is not just limited to the business of solid mechanics, rather it will be equally applicable to the business of fluid mechanics also. Okay, and wherever these kinds of stresses appear, it is equally applicable. All right, so how do we go about connecting the traction to the stresses? Before we can do that, I will quickly give you a brief recap of the connection between this traction and the various stress components that you have been studying till now, meaning sigma xx, tau xy, tau xz, tau yz, sigma yy, sigma zz. All these 6 stress components, what is this relation with this traction? That I will quickly tell you about. Most of you or many of you will remember this from your first year, but since this is so important, I will just briefly recap it. So in the previous page, we have taken an arbitrary cutting plane. We have not referred till now to any coordinate system. Now we are going to do that. So I'll just copy this thing. But now I'm going to set up a set of coordinate axes. Now, the cutting plane that I'm going to consider will not be any arbitrary cutting plane. Rather, it will be a cutting plane which is normal to this x direction. Rather, or in other words, it is parallel to the yz plane. So we take a cutting plane like this. Again, we consider the region 1 and region 2, and we focus our attention on the region 1, that is to the left of the cutting plane. So it is going to appear somewhat like this. By the way, in the previous page, I should have mentioned very clearly that when you end up with such a thing, you have to understand that this traction vector is not necessarily, okay, or rather I should say in the most general case, this traction vector is not coincident with the normal vector on that plane. Meaning that if I go back to this thing, to this diagram, and I draw the traction vector here, it will appear something like this, or in some arbitrary direction, but you have to note that the normal to this is like this. So this is the unit outward normal to the plane, and this is the traction vector. In the general case, they are never going to be coincident. In the special case that they are going to be considered, something very, very special, very special discussion will be required. We'll come to that later on. Okay, certainly not today. So here we have our situation like this, that the x is pointing out like this. So you please understand that this is our I hat, okay, or this is parallel to the x direction. And on this, just like before, we are going to end up at that particular point of consideration where we have drawn this thing, a traction vector. So it's something like this. This is the traction vector, maybe a little bit smaller. So this is our traction vector. Please understand that the traction vector, when we write something like this traction vector is dependent on two things. First of all, it is dependent on which point you are considering. Because if you refer to the earlier thing, all this discussion, it pertains to one particular point that we have chosen. Had we considered another point, we would have to consider a separate area around it. All the discussions that we had mentioned would follow, and you would end up with another traction vector, but which would be quite different from this. So different points would have associated with them different traction vectors. Another important thing which is associated with the definition of this traction vector is the choice of the plane. Because you see that if you consider this point, this yellow colored point which I have drawn here, back in this original diagram, it was somewhere here probably. And we had chosen to take a cutting plane which is passing through this point. But it would have been equally possible to take any number of other cutting planes passing through that point. Okay, it is completely our choice. We can have infinite such planes passing through that point. It is just our choice that we have taken this particular one. Consequently, we had the rest of the story developing like that. Now, as a result of a similar sort of idea, we are now choosing to take a cutting plane which is parallel to the YZ plane or which is perpendicular to the X direction. We have ended up with this green color traction vector, and you appreciate the fact that this green color traction vector is very much dependent on the point which we are considering as well as on the plane which we are considering. So if we had considered a different plane, this is not the traction vector that would have ended up even if we were talking about the same point. Okay. Similarly, if we were talking about the same plane, this vertical plane, but we talk about another point, we would not end up with the same traction vector. Okay, so this point or this particular issue associated with different points having different traction vectors, this is easily understandable to all students. What most students have a problem understanding is that at the same point, if you take different cutting planes, you will end up with different traction vectors. But that is a fact, and you have to remember that. If you do not understand that, none of the rest of the discussions will make sense to you. I repeat this, okay? So if you take at the very same point different cutting planes, then the same point may have or will have different traction vectors associated with it. So traction vector, ideally we should be saying that traction vector is a function of both the position vector as well as the plane. This is the formal way of writing it, but we don't have to keep on writing all these things. Okay. Now what I want to say is that all this is fine, but what is the sigma xx, what is the tau yx, what is the tau xy, what is the tau xz, all these things. So who can tell me if anyone remembers from their first year basic engineering mechanics? There is a definite connection of sigma xx, sigma xy or tau xy, tau xz, all these things with this t vector. Who can tell me?
Sir, sigma xx equal to t cos theta.
What is theta?
That is the angle
Sir,
between
theta is the angle between the traction vector and the x-axis.
Very good. So you're basically taking the dot product between the t vector and the I hat. Is it not?
Yes, sir.
Yeah. So what? So who said that? Who gave that answer? I cannot see.
Sir, myself, Jeevanjyoti, sir.
Okay. So sigma xx is equal to t vector dot I hat. Okay. What about tau x?
T vector dot J vector.
J cap.
J cap.
All right. Okay. Now you are saying that t vector is equal to j hat. Okay. And you will consequently say that tau xz is also equal to t vector dot k hat. This is fine, but you have to understand one very important thing here. First, when you are taking the component of this t vector along the x direction, that is fine. But once you take that, does it necessarily mean that the other component of the t vector that you would have to draw? What I mean to say here is that once you take the component like this, so this is your tx kind of thing. What I want to say is that the other rectangular component of this t vector perpendicular to this component, is that going to be along the y or the z?
So it will be the linear combination of both of them.
Exactly.
Combination.
Yes. So you have to understand that this t vector, it is not lying in the xy plane. Okay, nor is it lying in the xz plane. It is in some arbitrary direction. So what is going to probably happen is that maybe I should have drawn this arrow a little bit smaller, but no matter. Something like that. So this diagram is not very conveniently drawn. I need to make a little bit more space here. Something like that. Okay, so you understand that this is the thing. Okay, so here also, consequently, you need to understand that this is 90 degrees. Okay, this is 90 degrees. This is 90 degrees. Something like that. Okay, that is also 90 degrees. So this other component that is lying not along the y direction or not along the z direction. You have to take the component of that further along the y direction to get the tau xy, and further component along the z direction to get the tau xz. Or as you guys have already mentioned, you can take directly these kinds of things. But as you will see later on, for the more general case of a cutting plane, this kind of definition, there will be a little bit of a problem. That is why I wanted to emphasize to you that in general, the other rectangular component to it perpendicular to the normal direction, that is not going to be along the y or the z direction. Okay, so you understand this thing. Now tell me, what do I need to do to obtain the sigma yy, the tau yz, the tau yx?
So we have to consider
Take the different cut plane.
Exactly. So whatever we could extract from this cutting plane, we have extracted here. In order to obtain the connection of the traction vector with the other components of stresses, we actually have to go back to this diagram, remove this cutting plane, take another cutting plane which is parallel to the xz plane or equivalently perpendicular to the y direction, consider the traction vector on that at the same point, then take the component of that, and then we are going to obtain the various components associated with the y direction or the y outward normal. And similarly for sigma zz, we are going to take a cutting plane which is perpendicular to the z direction or equivalently parallel to the xy plane, and then proceed. So that's how we are going to end up with the 9 different components of stresses, which from your other studies, you know, equivalently it boils down to basically 6 independent components, because tau xy is equal to tau yx and tau xz is equal to tau zx and tau yz is equal to tau zy. All that is fine. So at a particular point, okay, at a particular point, refer to a set of coordinate axes, rectangular Cartesian coordinate system, we end up with these 9 different components of stresses. Okay, out of which 6 are actually independent. So we write like them, we write these things like this, that sigma xx, tau xy, tau xz, tau yx, sigma yy, tau yz, tau zx, tau zy, and sigma zz. And this can be actually be thought of as a 3x3 matrix. You may have heard of this terminology that stress is a tensor. Okay, so it is certainly true, but at this point I don't want to go into a formal definition of what a tensor is. Okay, we can discuss about it, or I can give you some notes which will give you some preliminary idea about what a tensor is, but they are certainly not part of your official syllabus, and I don't want to invest the time in a live session on that. But just know, maybe as a general knowledge, that a stress is a tensor of order 2. any vector which has three components, you know that will be a tensor of order 1. A scalar is a tensor of order 0. So this is just like general knowledge, okay? So a tensor of order 2, it is represented in terms of this 3 by 3 matrix. Not just a stress tensor, any tensor of order 2, it is represented by this 3 into 3 matrix. And for the particular case of the stress, this is referred to as the matrix representation of the stress tensor. Okay, sometimes in short, this itself is referred to as the stress tensor. And even further short, this entire thing is represented by this sigma, sometimes with a square bracket around it, to denote the fact that we are specifically talking about the matrix representation. Now, all this is fine, but we are still nowhere near towards achieving a connection or even taking the first step towards stress transformations. So what do we do? Well, what we do is, with this understanding that we have regarding tractions and the stresses, we go back to the general cutting plane that we had discussed in the previous page, this one. Okay. So I'll just copy this thing again. I'll copy this thing. Okay. Now, you see, I have this general traction vector, this unit outward normal to the cutting plane under consideration. And what I want to say now is that this traction vector, it can be decomposed into its components in at least two different ways. Okay, so the T vector can be decomposed into two ways. One of them you are already familiar with, you know that even without me telling you anything. One of them is that you decompose this traction vector along the X, Y, and Z coordinates. So unlike the first page of this presentation, we are going to set up our coordinate axis here. So this is X, this is Y, this is Z. And this T vector, it can of course be written as Txi hat plus Tyj hat plus Tz k hat. No big deal here. But there is another way. So this is one way. Other way is that we decompose the traction vector into a component which is not along any of this X, Y, Z, rather it is along this n hat. So this n hat is along some arbitrary direction. We just choose to take the component of this traction vector along the n hat. So it's something like this. Here. So this we call the TNN. This TNN, mind you, it follows the same logic in writing the subscript that you are already familiar with. So when you write sigma xx, the two subscripts x and x, they represent what? The first x, it represents, so if I write it here in the corner, the first x, it represents the direction of the unit outward normal to the plane under consideration, and the second x, it represents the direction along which the stress component has been taken. In a similar fashion, when you take the component of this traction vector along the unit outward normal to that plane under consideration, you are taking the stress component associated with that traction vector in the same direction that the unit outward normal is pointed. That is why this TNN. just like it was earlier sigma xx. This is not that hard to understand. The other one, the other component which is perpendicular to this TNN will be lying along this plane. So it's something like that. This thing. Now this we will refer to as TNS. You understand the first subscript here, the N, it refers to the unit outward normal again to the plane on which this TNS component has been taken. The second subscript S, it represents the shearing direction. Okay, so this component of the traction which is lying on the surface of this cutting plane, that is like a shearing component. So what we say is that this T vector, it will be decomposed into this TNN component which is lying along the N hat plus TNS which is lying along some kind of a shearing direction which is referred to by this ES vector or ES hat. So the ES hat is along this surface, but right now we do not know the exact specification of this ES hat. The only thing we know is that N hat dot ES hat is what? Tell me, N hat dot ES hat is what?
0.
Yes.
0.
Yes, because they are at 90 degrees to each other. All right. So as of now, it is enough for us to understand this. Furthermore, you note that this ES vector, you see, if you are looking at this cutting plane, there can be infinite number of directions which can be referred to as shearing directions. For instance, one may say that suppose I take this direction, suppose I take this direction, suppose I take this direction, any direction which is lying along the surface, all of them are valid shearing directions. But this S direction, this ES hat direction, it is a special direction which is not just perpendicular to this N hat, but is also lying on the same plane which is containing the T vector and the N hat. Okay, so this is very, very important to understand that ES hat is perpendicular to N hat and ES hat is lying in the same plane containing T vector and N hat. This is very, very important to understand. Okay, now what? All these are very abstract kind of mathematical things I'm talking about. Nice to hear, but how is it helping us in this in our journey of talking about the stress transformation? Well, it's something like this, that we want to make a connection between this traction vector and the stress components which we were talking about earlier with reference to the coordinate axis that we have chosen. So as soon as we take a set of rectangular Cartesian coordinate system like this or coordinate axis like this, we have already decided that we are going to have a set of 6 independent stress components called this sigma xx, sigma yy, sigma zz, and and the shearing components. That is true. As soon as you have chosen this xyz coordinate system, you have in your hand those 6 independent components of stress. Question that I'm trying to pose here is that is there any connection between this traction vector and those stress components? I repeat my question. Is there any connection between this traction vector, which I have considered on an arbitrary cutting plane, and the stress components which I had earlier obtained by considering cutting planes parallel to the or perpendicular to the various coordinate axis directions? Answer is of course yes. There is very much a connection. It's a very neat and clean connection, and it is one of the most important connections or relations that you'll study in solid mechanics. And all of this 45 minutes or maybe half an hour that I've been talking, it has been towards developing a motivation for this particular thing. And this is something, this particular relation that I'm going to discuss now, that is something which is grossly missing from our textbook of Beer and Johnson. In fact, most of the mechanics of materials textbooks or solid mechanics textbooks that you will find at the undergraduate level, especially meant for second and third year students, they are grossly missing this particular relation. Okay, they don't discuss it, but suddenly later on they will state something which will only be clear to the students if they know this thing. So there is a massive gap between what they are thinking, those authors are thinking, and what they are actually conveying on paper. So let's do this properly. Okay, so again, back to that question, that what is the connection between the traction vector considered on this general cutting plane and the stress components, which you have already seen in the previous page here, that these stress components are nothing like some of the special components of this traction vectors considering different kinds of cutting planes. Okay, so what we are basically asking is this. Okay, let me go to the next page and represent the question geometrically. Question is like this, that you are considering a point. Without any loss of generality, we can say that our coordinate axes are set at this point only as the origin. There is no harm in doing that. Okay, there's absolutely no harm in doing that. So we say something like this, that we have our coordinate axis like this, x, y, oh sorry, this will be z, y, z. And we are going to consider planes like this. We are going to consider a plane passing through this point and perpendicular to the z direction, like that. We are going to consider another plane. Let me draw this thing in yellow only. A plane which is perpendicular to the x direction. So these are all cutting planes that I'm drawing, okay? And of course, we are going to consider a plane which is perpendicular to the y direction. Perhaps it would have been better if I had drawn them in different colors, but no matter. So we have this situation. So three different cutting planes passing through the same point, and one by one, if you keep on considering these different cutting planes, you are going to obtain the three sets of different stress components. But there is still one plane missing, and that is the general cutting plane that we had talked about earlier. So let's draw that cutting plane, maybe something like this, which is obliquely oriented. But very importantly, this general cutting plane that I have just drawn, that is also passing through this yellow colored dot or the origin. So we are considering four different cutting planes. Okay, three of them are perpendicular to each of the coordinate axes, and one of them is along some general direction, but all of them are passing through this yellow colored point of origin or the point of concern. Our intention here is to establish the connection between the traction vector, which will be appearing on this orange colored cutting plane passing through this oblique general kind of orange colored cutting plane, and the other stress components appearing on the other cutting planes. Okay, so what is the next thing to do? What we do is that we will fall back on the fundamentals of mechanics to establish this connection. Fundamentals of mechanics means we are going to consider the equilibrium. But what equilibrium are we going to consider? The only body, if you can even call it a body, is this origin, the single point that you have considered. Okay, what equilibrium are you going to consider of this single point? That doesn't make any sense. Okay, of course it makes sense, but it doesn't seem very hopeful to make some connections or establish some relations using just a single point. So we will do a clever little trick here. Okay, this is a master stroke actually, and this master stroke was given by a mathematician, a very famous mathematician. So back in I think the first half of the 19th century. So his name was Cauchy. Okay, so Augustin Cauchy. He's a French mathematician. Perhaps in your studies of fluid mechanics, you may have already heard of something like the Cauchy's equation of motion. If not, you are soon going to hear about it. Okay, so all your Bernoulli's equation, the Navier-Stokes equation, they can be derived from this general Cauchy's equation. In fact, the Cauchy's equation of motion is so very general that the equations of solid mechanics are also equally derivable from them. In fact, the Cauchy's equation of motion are applicable as long as it is some kind of a continuum level body. All right, we don't have to go into all those mathematical histories. You just appreciate the fact that it took a little bit of a mastered stroke of a genius to come to this little trick. And this trick is so very elegant that we can actually discuss this at the second year level. Okay, so it's something like this. We have all been talking about at a single point. That is the correct thing to do. But the trick is that you don't consider this at a single point. Rather, you consider an actual solid body. How do you consider a solid body? Just change your perspective a little bit, and instead of considering these planes or this third or fourth plane, the general cutting plane, to also pass through this origin, you take it at some distance away from the origin. Okay, so just like before, you keep on considering these yellow colored planes which are perpendicular to the three different coordinate axes as they are. Keep on doing that. But this fourth plane that you are taking, you don't consider to be passing through the origin or that point of concern. Rather, you take it some distance away from the coordinate axis, so that this cutting plane will actually cut or intercept this x, y, and z axis at finite distances. So what is the shape that you will end up with as a result of the intersection of all these four planes? Quick maths quiz. Tell me.
Pyramid.
It's a pyramid. Yeah, it's a pyramid. What's the proper terminology for a pyramid in 3D solid geometry?
So triangle based.
You are forgetting the name. Who can tell me the name?
The tetrahedron.
Yes, tetrahedron. That's it. Yes, good. But pyramid is also fine. Okay. So it's something like this. We again draw the coordinate axis. We have our cutting planes, but this time I'll draw them in a cleaner fashion. This is the plane perpendicular to the x direction. This is the plane perpendicular to the z direction. This is the plane perpendicular to the x direction. And this is the plane that is the general plane. Okay, so you see how our tetrahedron has shaped up. So ultimately, it is this tetrahedron that we are talking about. This is the tetrahedron. We don't have to worry about all the other planes and everything. Okay, so just this entire tetrahedron. That's it. Now you tell me, in the little time that we have left, and now I have got so much tempo in speaking the rest of it, I don't want to end this class, but I have to. But anyway, before I end, you tell me on this thing, I can draw a, so it's a little bit difficult to represent it in this diagram in a three-dimensional way, but you understand that when I draw a vector like this, I really do mean that this n hat is perpendicular to this plane that I have just drawn. Okay, please try to appreciate it. This is perpendicular to that plane. And the traction vector which will be appearing on it, it will be along some arbitrary direction like this. Okay, now I'll quickly copy this thing, go to the next page and ask you to answer a few questions. Very quickly you try to answer.
Sir, this triangular surface is the section which we cut, or something other surface?
Yes,
Some other
that's a
surface.
general cutting plane.
Sir, but if this cutting plane pass through this origin, then how can it cut the x, y, and z axis, sir?
What did I tell you? All this discussion about Cauchy, did you not listen? So I told
Sir,
you
listen,
that,
but
yeah, I told you that actually this orange colored cutting plane should pass through the point of concern. But we want to establish this connection between the traction vector and the other stress components. So how do we go about doing that? So the trick that was given by Cauchy is to consider this cutting plane not through this point, rather at some distance from that point. And we are going to take the limit that the height of this tetrahedron is going to 0. That I probably did not mention. Okay, eventually what we are going to do is we are going to do all our mechanical equilibrium business, and at the end we are going to say that in the limit of this, the height of this tetrahedron going to 0, this plane will again go back to that origin. Now it is some distance away from the origin, but if we say the height of the tetrahedron goes to 0, the plane actually moves closer and closer to the origin. So we'll be back in this diagram. Okay, so we have taken this kind of a finite dimensional tetrahedron with the intention of finally eventually taking the limit of the height of this tetrahedron going to 0. Does that make more sense now?
yes, I understand, sir.
All right. Okay. Yeah, it's my mistake only. I did not mention that limit of height eventually going to 0, but I wanted to keep it like a little bit of a detective story that eventually I will reveal to you that what the great trick is. But anyway, it's good that you asked me. So in the 1 minute that I have left, what I will do is I'll quickly draw, or I will isolate out the plane which is perpendicular to this x direction, and you tell me the components of stresses which are appearing on that. So what I'm going to do is, you see, this is my origin O, this is, let's say, A, this is B, this is C. What I'm going to say is that I'll concentrate on this triangle OCB. Just isolating it out, okay, for the sake of clarity. So this is triangle OCB. On this surface, looking from the other side, you tell me what are the different stress components. The easiest one I will do myself. This is our sigma xx. You tell me the two other things.
So sigma xy.
Sigma
Delta
xy
X.
downward.
Direction.
Very good. Whoever said downward, well done. Okay, so the tau xy will be actually downward. This is tau xy. Why it is downward? Because we are considering a plane to which the unit outward normal is along the negative x direction. So the shearing stress must be such a way that it is pointing opposite to the y direction. In a similar fashion, your tau xz will be in the opposite direction of the z. So this is tau xz. We are going to talk about the other two planes, triangles OCA and triangle OBA tomorrow. And we are going to consider the equilibrium, and very quickly we will establish the connection between the traction and the stresses. All right, thank you very much. Please go to your next class.
Thank you,
Sir,
sir.
can you recommend the reading part from which we can read this?
I have some notes from your senior batch, but I taught them in a very general fashion. I'm most happy to share it with you, but you will see that you'll have to read quite a bit to understand this very same thing which I'm trying to teach you in the simplest of fashion. Okay, so either it's a very hard textbook or it is Beer and Johnson, but I have chosen to make this lecture notes in such a way that it's at a reasonable way for you guys to digest. It's not there in any textbook, to be honest. Okay, so
Okay, sir.
But I'll anyway share those earlier notes with you. Okay, but those are officially not part of your thing, but anyway, I'll share.
Thank you, sir.
Yeah.
And so please,
Thank you, sir.
The tutorial sheet 3, sir. Please upload answers of this. And some solution.
Sorry.
Sir, solution of tutorial 3, sir. Actually, I'm
Yeah,
getting
we-
difficulties.
Yes. We had a discussion about it earlier, right? So give me some time. I'll try to come up with it.
Yes, sir. Thank you, sir.
Yeah.